Now we will talk about potential due to a continuous charge distribution, and we have an example of charge disk. Uh, Before I go over these, I want to go back and explain, but that's the page we're on. So I want to write it here so we can go step by step. So step one, first of all, we're finding the potential at this point P. You can see that it's along the central axis of the disk. So the object, the charge object, is this disk you see here, and the disk is made of those orange rings, okay? And that R prime, as shown here, is changing. So if you want to make a disk, you can start from the centered 0 R prime, and then you can go all the way to the capital R. And you just need to add all the contributions coming from them, and you can get the potential equation. So what we're going to do is, first of all, we will start with writing dq. So remember that q, the charge, is the charge density times the area. Okay, and we are focusing on the ring, so we need to think about that. So we have dq, and we are writing it for that, and dq is the charge on this very, very small ring. But it has a thickness, and that thickness, as you can see it on the figure, as given as dr prime. That's the thickness, and r prime is the radius. So what we're going to do is, again, writing this infinitesimally small charge, dq is equal to sigma dA. So this dA is the area of the ring. So we need to think about that and write that in more detail. So that is sigma. And dA here is the area of the ring. So if you open up that ring, so I'm just gonna kind of draw it here. Think about that, I cut it somewhere here and then open that up. It's gonna be something like this, right? So this is gonna be, the thickness is again from here to there is dr prime. And this side is gonna be the circumference of that. So it's gonna be 2 pi r prime. So to find the area of that, right here, that orange area, you can see it on the figure. That's the kind of rectangle, so we're going to do that 2 pi r prime times dr prime. Okay, that's where that dA comes from. So dA is 2 pi r prime dr prime. So that's our infinitesimally small charge. In step 2, we write the potential. But again, the way we will write this, so I'm going to write that K, which was 1 over 4 pi epsilon naught. V is KQ over R, right? Since you're writing dV, and since it is a charge distribution, it's not a point charge, so you need to write your Q in terms of dQ. If you write a dQ, then you're going to get dV, not just V. So that's the change we make. And then that's equal to, again, 1 over 4 pi epsilon naught. And on the right side, so we have that dq, and we have this dq here, so we're just gonna substitute that. Let's do that. And now we will think about that r at the in the denominator as well. So dq is sigma, my sigmas don't look good, sigma 2 pi r prime. Dr prime is the area, right? So this is really sigma dA divided by r. What is r? R is given here. We will be using some geometry. You can see the right triangle here. R is kind of the hypo. So when we write r, we're going to write the square root of z square plus r prime square. You can hopefully see that triangle here. And you just need to square the sides and add them up. And that's what we have here. So down here we have z squared plus r prime square. And that prime definitely does not mean a derivative. Okay, it's just we are out of r's. We use a little r, we use a capital R for the radius, so we need some other r, and we are using capital R prime as our variable. And then what we do is, again, we have infinite number of rings that makes up this disk, and we're going to add up all the contributions coming from them. Okay, so This is like thinking about that R and writing that is kind of step 3 because that's coming from the geometry, right? And step 4 is really plugging it all together. So this is kind of step 4 here. Once we put them together, combining them. And so at this point, what we're going to do is we're going to do U substitution. So it's much easier integral than the previous case. So we're going to say let U square is be Z square plus R prime square. So I'm going to let that, what we have in the root, to be U square. And when you do that, when you take the derivative of both sides, you got 2U du, and that's equal to, since z is constant, that goes away, and r prime is the variable, so we have 2r prime dr prime. Okay, so that will be very useful. You can see that 2r prime dr prime at the top, right? So we will be using for that. We will be substituting them. So let's just write step 5 now. Let's put this down a bit. Okay. And next, we are integrating both sides. Okay, so we will kind of take out the constants. And you can see that this 2 pi and sigma are constant. We will take those out as well. And 2 pi will really go away with this. It's going to cancel out, and we will have 2 at the bottom. So what we are having on the out of the integral on the left side is v, dv integral becomes v simply. On the other side we have constants sigma over 2 epsilon naught so far, right? We put the sigma out, cancel those 2 pi and 4 pi, and epsilon naught was there too. So what happens to the rest? Let's write it down. R prime dr prime, and that becomes, you can see it here, so let's cancel these two as well. So I have r prime dr prime right here, and that is u du. Okay, so that becomes u du, and that is divided by, remember, z square plus r square is u square. So we're gonna also put this in. When you do that, you take the square root, so you get u as well. Okay, and this integral simply turns into, so u's are going to go away, simply du integral, like dx integral. Okay, you just get out of this, you get u. And so let's write that down. So we got sigma over 2 epsilon naught u. Okay, and then we're going to say we got u square as that, so u is going to be, so sigma over, and this goes from u initial to u final, of course. There are intervals that we need to put in. I'm not going to worry about the intervals yet because I'm not going to do it for u. I need to convert back to z square plus r prime square form. So let's do that. So first of all, we just need to write the function u, and that is root z square plus r prime square, right? That's how we defined it in the beginning. And now, since it is in terms of r prime square, it's not u anymore. And think about how we integrate this. We are starting at the center. That means it starts from 0. It goes all the way to r, and then it's going to go from 0 to r. And that is for r prime. Okay, so let's do that part. Sigma over 2 epsilon naught. When you substitute with r, you get z square plus r square. So r prime goes to r, and that's what we have. That's the first term, minus. So when you put 0 for r prime square, and that is 0. Let me fix that. And when you put 0 for r prime square, that term goes away, and then you get root of z square. Z square comes out of z. And that is the answer, and that's the potential due to a disk at a distance z. So then we can say that, I'm just going to go back to the notes. As you can see, the box here, we have the same answer as we have it on the notes. just want to show it in detail.